Hello guys, welcome to my channel Network Simple. Okay, so wireless signals, this topic is completely new to me, so I'm gonna start searching about it, and the way I will understand is what I'm gonna show you guys. So let's go. Okay, so these are the main topics that it's talk about in the slides: amplitude band, carrier signal, DBD, DBI. So let's go one by one what it means. So the first one is this dB decibel. dB is not a power, it's not a signal, it's not a. So dB is a way of comparing, it's trying to give a measurement of comparison of the electric signal. And this is the example they give out. So how do engineers use this? So to calculate the differences, what is a small and what is a large, they use dB in this way, plus, minus, and zero. And this is the example. And this is the definition they give out. dB is a logarithm between two power or signal if that's filler. So we are comparing one signal with the another one. Okay, so this is the first part they give out. Important dB rule laws to remember. Multiplication becomes addition. In normal numbers, 2 into 2 into 2 equal 8 plus dB 9 dB. When things multiply in real life, you add them in dB. This is the most important rule. Why this matters? Wireless links are full of transmit power, antenna, cable loss, path loss. All of this multiply in reality. Using them, you just add and subtract, much easier. Okay, so we have low one. Multiplications become addition. 22 into 2 plus 3, 6. You just add and subtract, everything is added. Antenna again. Plus dB, plus dB, amplifier loss in negative, gain in positive. Antenna gain, plus in positive, low 2, loss in negative. Gain, loss is negative, gain is positive. Okay, simple. Distance, path loss, simple. They kept it. Good things add, bad things subtract. Okay. Nothing. 0 dB means no change. Plus 0, it means nothing change. Okay. Is this again or loss do I need? What is my reference point? Okay. There. Is this a gain or loss? Do I add or subtract? What is my reference point? Tiny example. No math. Transmit. Antenna gain 5 dB. Okay. And this is the main dB is only it's only compared if you don't know that. So the was to compare level in telephone line. The reference was another power level. dB was invented as a power levels in the telephone line. That's why we add suffixes unit dBm, 1 milliwatt, 1 watt, isotropic. Without the suffix, no, okay. And think of it, the signal is 10, this is 10 units taller than watt. dB is a relative and equals a reference to have a physical comparison. dBm, dB comparison plus reference. Differences define what final mental difference define what 0 mean EIRP. Why dB becomes okay. because it is and so what this reference later everyone calls 0 once that agreement or compare become on this what it makes the eligible for something where it must be for realizable 1 milliwatt can be generated in an amp somewhere not except it should not change over the time a battery voltage 1 milliwatt per hour. So this is the reference. Two labs on opposite sides of the world must be able to recreate it. Any lab can generate. Okay, it's simpler. The simpler, the less will be 1 milliwatt, 1 watt. I tell you so why this specific references why dB and why milliwatt is enough for RF radio frequency, but not this one. Easy to generate and very convenient scale for radios. Why dBi uses isotropic. Why isotropic cannot be built mathematically perfect. Why DBD exist in a real half dipolar cell builder common energy who decide the standards internal over longer through industry example. Everyone uses the same reference so results become if it is true because it is a okay. Okay, we'll start with the EIRP. EIRP, how strong your transmitter looks to the wall in the strongest direction. It's not just it includes what the antenna does. How strong your transmitter, meaning the transmitter. The EIRP when you work in the DB style DB and EIRP EIRP okay it's not saying well, how many TX power what the radio outputs antenna again wait the equation this TX transfer the device the electrical power that the device outputs there are another applicable transmitter radio access point radio phone radio generate or radio transmit power measured in dB or this is the power before this transfer outputs to the antenna is separate component does not create power it only shifts and directs power antenna does not they just redistribute it it's dBi not dBm put it together EIB transmitter loses some power in cables connected antenna focus dBi the antenna transmitter the transmitter output just effective isotropic radiated power isotropic is the power would need if the same equivalent isotropic power isotropic power radiates in a equal so will like a perfect signal isotropic power okay so iso donut shape perfect okay why engineers direction okay, same perfect as zero reference that's what you say antenna type isotropic perfect sphere deep dipole donut shape focused beam okay isotropic that's so isotropic means in ER so isotropic means in ER equal or direction forward clean as means the power is radiated to avoid it does not mean your real and repeating so we can compare as the power is radiated we face in exam safer if you want the model express the equivalent that would be real antenna flashlight isotropic beard light bubble equal everywhere how bright would the bulb need to be to match the flash in its okay so let's go to the isotope so let's start the IRP when you work in the DV style there the power, Tx bar, the antenna power, no, the device power, and the antenna gain, cable connector, cable focusing like flashlight. Okay, 1 tiny not red, 20 degree antenna gain. So antenna gain, how antenna redistributes power in space. When you see antenna gain compared to a perfect isotropic antenna, there's antenna concentrates energy, so that signal is 6 dB stronger in its what it means. The tunnel 6 fixed amount of the pushes less in some direction, pushes in another is the same. No nozzle water space isotropic narrow. So that shape Y gain is in dBi, not dBm. Very stronger signal is chosen. Antenna gain represent the program already compared to ISO. Uh, so the antenna to the physical height or length intensimeter is not 10 dBi. Okay, it feels bigger antenna equal more gains, sometimes correct but not gains is about not says what antenna gain actually depends on antenna gain, antenna dipolar patch, Yagi, geometry and show how current flow, not height, thick, likeness, Wi-Fi stick antenna, 12 centimeter, 2.4, 2 dB, 2 to 3 dBi, 12 is not equal to 12, equal to maybe 8 to 12, 30 dBi. Mm. Okay, okay, 30 does not very strong. In one specific, the signal is 30, then an idle. 30, 30 will magnitude extremely focus extremely. So this is antenna gain, horizon, vertical, horizontal. Along a points to microphone push all into narrow beam. What antenna gain really? This is antenna gain. How narrow? The radiation pattern as white pattern. Okay, white. Is this the white pattern? White pattern. White pattern low dBi, narrow pattern high dBi. Nothing else. Okay, good. One high dBi. Long distance links. Satellite camera when you know where they where so why high dBi mobile Wi-Fi is in too wide, medium, narrow. Oh, so refined phones laptop very narrow. So we can visualize dBi as a ball being squeezed. The more it's squashed, the more its sideways increase. It becomes wider. we just need your idea design is not create. It's just about the same. Not creating a is a good starting. The correction. The more it's good, the more for hiding it actually the perfect energy goes everywhere equally. The ball is squeezed from the not the top bottom from many direction arrays into fewer direction. Think of a not of oval ball, long, thin, higher dBl. Okay, this is a being sector memo. Why visualize this? Okay, this is the low dBi, then medium dBi, okay, and this is a isotropic energy goes up, down, left, right, everywhere. Then balloon floating mental very perfectly meaning maximum light squares oval balloon. Okay, shape donut energy is reduced above and below sideways from top and still a wide coverage. Better range horizontally, typical Wi-Fi access point. Hard squeeze, very sharp. Okay, so this is the dBi. Free space. 99 again will go free space. The core idea of free space, just because it spreads out. No walls, no outside, just distance. Okay, radio frequency carrier 1000 amplitude modulator. This is how much of sound by my sound amplitude modulator. I think amplitude modulator means that it will carry and translate. Amplitude modulator carrier. Okay, so it's sending the signal, but it's not the translator transmit. I'm telling the ChatGPT to explain me simple way, and but it's showing me this Frenzel zone. What is this? Free spread. This one, I think this 40 dBi, 47 amplitude beam, minus 40 dBi, 6 dB, 1 meter, 2 meter, 40 meter, 47 is the first meter. Okay, I don't know. The antenna sends energy out the wave, expands like glowing sphere. So at any of the signals, nothing. And the distance is the distance, the signal, the reduction in signal strength. Longer the part, the more the loss. Even in Vega, the signal still weakened because of geometry, not resistance. Okay, distance increase loss, double the distance, much weaker, triple the distance, even weaker. Higher frequency 2.5 travels farther, loses strength 5 gigahertz, loses strength. Microwave wave millimeter wave losses. Higher frequency energy spreads more tightly, more loss per distance. Um, More loss per distance. Loss increase in frequency, loss increases. Loss, okay, 190. Phase 5 is the reduction in signal strength caused by the electromagnetic wave as they propagate through free space. Signal strength at receiver, free space, path loss. Signal at reflector depends on EIRP. High transmit power will still kill the signal, but will a small close to antenna strong small balloon as it moves thinner surface weaker, same energy larger area. The more it's squished, the more it okay correct. Does SSP happen with that? Yes, if that's clear we can. What were the diagrams about? Yes, route equals it becomes weaker modulated amplified carrier wave. What is this? Incident. How do I understand this? Antenna is the center, circle or sphere, getting diagram expanding circles, getting bare as they go out. Circles are getting bare, antenna is the center, circles are getting as a vertical. spreads in aura, increasing strong signal close to antenna, weak signal far away. Close to fire, amplified carrier, wave, transmitter. Give me one word synonym for them. So this is how I try to learn sound waves, voice, sensor, microphone, sensor, modulated waves, the modulated carrier encoded, strengthened, okay, amplified, okay, audio amplifier means it increased it, okay, we can see it shorts, then it increases, okay, audio amplified, amplifier booster, amplified louder, radiator, if you want, encoded, engineering, boosted, powered, imitated. Encoding for is changing that. So it can be here that in the context of your diagram, your voice cannot travel far. The carrier wave can travel far, so we encode it into the carrier. So we make the carrier wave change into a controlled way to represent what is actually changing. When we modulate, we change one or more height, speed, timings. Those change very concrete thing of mirror dot dash. The parameter. Okay. It's not making adding a changing structure pattern. Okay, let's go. We understood this one. Now what about this? What is incident high order Bessel vortex? Ignore inside incoming wave. Special wave twisted. What twisted? Ring like. Okay, the wave is like it's a specific shaped incoming wave. This is just an incoming radio wave. Homologous evolves same material through the object the wave hit. In real, this could involve any obstacle. What happens when the during some energy continues past, then it's scattered equal redirected. The wave bounces, deflects. The wave is not there; it's redistributed. Signal strength changes. So these are just Cora used to do where the scattered goes. These are not the Cora. Engineer using at this end the signal look like this. Why is there not? Okay. So we finished this part. Okay. These are not mathematical. Keep it simple exams. What it first? What effective range means? The distance where the signal. Okay. Of transmitters. Transmitter means receiving. Maximum detectable 2.2 lower data range. Higher data. Okay, this is the signal. It can surround this much. Lower data coverage, higher data coverage. Higher data rate, smaller coverage area. Okay, so it covers this lower data rate. Okay, that is where the still maximum detector but stronger for reliable. Lower frequency, longer range, higher frequency, shorter range. Okay, okay. Free space parallel, higher frequency, lost time with distance. Space and weekends faster than longer wavelength bands and penetrates wall better, shorter gets blocked. more easily. Dual slow, heavy waves travel further, pushes through wall. Okay. Interference lower, higher, more crowded, cleaner. Perform coverage for coverage. So 2.5 is for coverage, 5 gigahertz is for performance. Room next door still strong, weaker or gone. Faster but slower. Whether this is becomes another can be understand. Effective range transmitter, the radio device that generates and sends the Wi-Fi access router exam. Okay. Because Y transmitter, but the sense frequency not under RF propagation into this. Okay. The most modern Wi-Fi. The more controller one for multi-band radio, one operator so the same day can either but does not send on the same unless it has separate radio. But, one device, two bands for the same device, same transfer, same antenna type. So we got that it's for the coverage. Okay. So I'm getting every concept right now. I'm really happy. Example of receiver sensitivity level now. Example of receiver sensitivity. Okay. This topic is the receiver sensitive. What it means receiver is the because a receiver can. Okay, so that 1 bar signal from the Wi-Fi. Okay, loud voice quest. Is it okay? How is it expressed? As of 1 dBm, it's okay, okay. Receive if receive 90, it works. Less greater than 90 dBm, minus 90, it works. Less than like minus 90 dm. If it's above the 90 dm, so it's good. But it goes to 100 minus dBm, it's bad. Example, it's got RSSI. Okay, I understood the signal. Example, medium, low speed, high speed, typical sensitivity, EIRP link fail. So sensitivity is meaning link fail. Yes, and you're saying that the failures are one failure hence okay. So example of receiver failure threshold. How good the in general, how weak signal greater than the pass less than sensitivity fair. That's how it's exactly used. So wireless signal at the receiver time. So sensitivity is this is the okay. So this is the great example. Okay. Okay. Modulation scheme output. How much data, how much speed the radio can, so how much data the radio can successfully send using specific modulation. Concern 1 gram. This is how data is encoded onto the carrier. What is the on? What is a carrier? Is it like phone or something else? Exam BPCK, simpler, slower but robust. Complex modulation output, the resulting slower but robust, simple modulation, complex modulation, simpler, complete, half faster but more fragile output means the resulting data rate, the bits per second you actually get. No. This I'm starting to not understand what it means. This by wave uh, data like rate star bits per second. How much storage of which is created? How much data is created in this second? Better how period easy to multiply. Um, well, the diagram. Okay, let's see. What is a wave? Carrier a wave, not a device. Slightly cleaner router device, slightly phone router carrier a radio wave created by the device. High frequency carrier wave. Very simple. These are the types of modulation encodings. Simple, better, faster, faster. Then some more complex, more data needs cleaner signal. What do you mean by cleaner signal? Modulation changes the wave to carry the information. Modulation encoding, modulation imprinting, shaping. Encoding is the best way to capture the output equal to not voice specifically. Examples of output calls data information. What does the data rate here means? Speed, not rating like data speed. Bits per how many each second? 1 MB, 1 million. Okay, data how fast information comes out from the transmitter. Modulation scheme how so rewriting a modulation scheme in the you actually how fast the data really arrive. Mm. So this line means how fast the modulation sends out data, which is according to the data to the transmitter. How do I know? Uh, it is the full form. Uh, Cleaner signal, less noise and distortion. What is this? Less noise and distortion. Any analogy? What noise interference? Started unwanted random anything that confuses is much stronger. High signal to noise ratio. The researcher can tell the symbols apart. big letters. Think of letters. Very complex modulation needs a big letters for easy to even prepare. Okay, modulation basic. Tolerant to you're saying about the let's yes, how far. Yeah, you can just data race is how fast encoded. Data is from transfer to the receiver. Okay, to the receiver like amplified. Okay. Send data. That's uses. Okay, full form of here the binary phase shift keying, quadrant phase shift keying, quarter amplitude modulation, height modulation. Okay, 16 possible ways, 64, 256 possible ways. Basic binary quadrant. Okay. Uh, clean the quiet room 1% talking you hear every word. Noisy say many people musics. Okay. Voice equal signal other sound. And a phone call quality clear voice no static. So hello. So you say what some this is what happened in 2 bits. So signal to noise ratio. So noise adds randomness to the signal what distortion. So what are the noises for them? What they differentiate? What is that noise? Noise and randomness. And what is the signal? Said you are still readable. Simple. Let's noise shape show icon. Okay, let's go. Other they send real file but not meant for to your user. They are noise. What are these noise? Other Wi-Fi networks. Signal for them, noise for you. Uses Bluetooth radios to some air sometimes different timing. Bluetooth energy equal now micro oven. Not any just run random electronic CPU emits small RF in additional radio background electrical noise. Okay, thermal cause bias. So how does the result also show that knows what to look for? Frequency, timing, modulation, and symbol structure. Your signal has a structure, noise does not. And your name in a crowd? Okay. I'm getting something. Signal to noise intuition is the pattern storm. So it follows the pattern. Why some patterns file. So so this has so each of them have a pattern and it tries to match. So yes, you're thinking the key is when show only some of them, how others are the receiver does not try to it tries to match one pair and it's let's go through one. Other they have patterns. They are valid files. Follow different network, different timing, different data structure, but not treated as noise. But not talking. Yes, it has patterns. Okay, so they have pattern and they, but so in short, the result does not allow, it only checks whether the expression stands out clearly or in short, does it have a pattern? Does the signal have a pattern? Does the receiver signal have to accept the transmitter and then differentiate the signal to noise? Just ensure knows the exact of the time and accepts the another. Okay, let's go. Summary of the so each amendment improves speed. Wi-Fi 1, Wi-Fi 2, faster, shorter, Wi-Fi 11 to standards, Wi-Fi 11, and do these words Do this word have meaning or anything shorted for B, A, G, and A, C, A, X? Efficiency in smart 2.4 Wi-Fi. What Wi what adding numbers to Wi-Fi means? Low range. What one slow variant and speed over range. Big introduce. So they do not stand for words. They are just labels. What they actually are, they are amendments in the chosen as for the newest version. BJ version and nothing more. There is no basic advanced in it. These letters are literature, not abbreviations. What does this numbers to Wi-Fi mean? Wi-Fi for simplified marketing. The exam Wi-Fi user and Wi-Fi for AC, Wi-Fi 5, 6E, gig 6E. Why this changing income? Simple. Okay. Generation say Wi-Fi numbers do not. Those Wi-Fi it's not. They mean you're there with better technology, internal standard Wi-Fi number, human friendly. Okay. Now I understand some part. Faster than B, faster. So 2 point. So this is the 2.5. So improving the 2.5 gigahertz. So this is what the Wi-Fi 1, 2, 3, 4, 5, 6 means. 5 gigahertz is AC very fast. Okay. Better be in a big milestone in your broadband. Okay. 11 and 2.5 and 5. Now they are using both coverage. Okay. So same together much less, much more clean. Okay. Good. Good. Here's a shifting. Here's a distance increases as function of increases. As distance increases, vital or as take a okay. Function dynamic shifting as a function of range. Linkage signal strength drops, noise stays roughly there. SNR gets worse, starts making errors. Okay, what dynamic means in here? Automatic continuous happen. No user exam. Share transmit via modulations. Okay, the distance very close. Okay, dynamic simple step very close, medium very noisy. Q. Okay, dynamic lower rate shifting. Dynamic automatic uh, automatic slow or referring to the distance referring to going far from the antenna referring to the going far and slow or fast function what it's what it's doing range the zone of 2.5 and 5 gigahertz. Am I saying this correct? You are almost there and we just nailed that. So then there are other automatic while conditions distance is small but not the okay. Slower for when rate data speed not physical. How fast the data? This is the confusion. Your question is what function means here. Define rate as a function of a no math range the zone. It's like the distance between the not transmitter and the receiver. Dynamic rate shifting means the data automatically. Can you change? Uh, when you're talking when your friend is telling you you can speak fast, further you slow down and speaks more clearly when your friend distance range high data rate, so low data rate. Speaking simple modulation, automatic design. Now dynamic rate Wi-Fi automatically so that when you move further away. Okay, let's go. Uh, So this is the first slide, and we just finished understanding all these terms. What does the multiply when things multiply you add dB, so when things divide or cause loss you subtract, minus loss gain equal loss minus a gain, zero means nothing. How do you wow. Okay, so this is all for this first slide. Then moving to the next, we'll go to the next after this.